Okay. Okay, the last session closed just with a lot of delay. Then I just waiting 2 minutes and we will start. I just would like just only check if there are all the speakers. Erwann Quimbert, Eero Hietanen, yes. Berg, Sonne, okay. Edgar, there's no one about it. And Xabier, Erana, okay. Probably we are missing one presentation because there's no presentation, no person, then I don't know what. Just a few notes for all the speakers. You have to compile this form for video and recording, okay? And just we have 4 presentations, not 5 it seems, because it's missing one. Okay, 15 minutes for each one, and then okay. Edward, Quimbert, it's yours.
We begin? Good morning, everyone. My name is Erwann Quimbert. I'm from the French Marine Research Institute, and I'm going to present you some initiatives originating from the Indian Ocean concerning the needs for sharing and promoting the spatial data into many partners into a global spatial marine data infrastructure. This map illustrates the surface area of each country around the world according to their exclusive economic zones. As you can see on the map, France appears as the second largest maritime area in the world because of these overseas territories. We have slightly more than 11 million square kilometers of EEZ. 1/4 of the French EEZ is located in the southern Indian Ocean. In 2009, French government has defined a national strategy for the ocean based on the maritime dimension of French overseas. This national strategy has been written into the Blue Book, which gives the French vision for the next 20 years. As stressed by the Blue Book, the National Blue Book, the southern Indian Ocean, extending over some 22 million square kilometers, is where the French maritime policy can have a pride of place. In this context, in 2011, the Southern Indian Ocean Blue Book has been written. It describes and recommends a number of strategies for the relevant authorities to carry out in specific fields. In this slide, I just wanted to give you some information about the IFROMER delegation in the Indian Ocean. We are based at the port in La Réunion Island, which is located at the northwest of the island here. We are based in La Réunion since the 80s. Some key figures I don't want to. We have some premises, and the main partners of IFROMER in La Réunion are listed here. We worked a lot with Berg and ERD, as well as with the University of La Réunion. The geographic area of competence of delegation of the IFROMER delegation covers the French EEZ, the French EEZ of La Réunion, Mayotte, and the Epars Island, which are represented here, represent slightly more than 1 million kilometers, and the French southern and Antarctic territories here represent 1.7 square kilometers. As all the coastal sites of IFROMER, delegation of La Réunion has the following main mission: to acquire data and knowledge of the marine environment, to manage and synthesize data and knowledge so as to make this available into a database, and to prepare advisory notes, give expert advice, or aid decision making for the sustainable management of maritime areas. Into this context, in 2011, the Prefecture of La Réunion, Mayotte and TAF decided to set up a marine spatial data infrastructure, which is coordinated by the DMSOE. DMSOE stands for Sea Office of the Southern Indian Ocean. The objectives of this marine spatial data infrastructure are to gather data sets related to the state intervention at sea, to establish a geographic reference essential for the implementation of maritime policies, and to encourage and facilitate the shared management of spatial data. To set up this MSDI, they decided to use the French MSDI, which is Sextant, called Sextant. Sextant is composed with three main components: the metadata catalog here, which allow users to search data, the GeoViewer, allowing users to display data, and the basket here, allowing users to download data. All this infrastructure is based on open source software mentioned here. Thanks to the Remata project, other local initiatives have been set up in the La Réunion Island. I will give you some of these initiatives, but I won't be too long for each of them. The first one was Polmar Réunion, which represents an atlas of coastal sensitivity to marine pollution. It's a project coordinated by the Prefecture of La Réunion. At the moment, we have 45 metadata in this catalog. The second one, it's a catalog dedicated to the RNMR, which stands for Réunion Island Natural Marine Reserve. At the moment, we have 30 metadata in this metadata catalog. The third one is the Shark project, coordinated by IRD. It's about ecology and habitats of two species of coastal sharks in La Réunion Island. Then the Torsoy project, which concerns the sea turtles in the Indian Ocean. We have actually 6 metadata and data about these topics. This project is coordinated by the Observatory of Marine Turtles, Colonia. Then we have the Globis project, which concerns the population of cetacean of Réunion Island. And finally, the GMAIL project for integrated coastal zone management. This project will begin in September and is managed by local authority. All these initiatives lead to the establishment of a regional portal called Sextant Indian Ocean, which can be considered as the first marine SDI in the southern Indian Ocean. This MSDI has the following objectives: to avoid duplication of data, to overcome barriers affecting data availability, to improve quality of geographic information, to make data more accessible to the public, to establish key partnerships in order to increase the data availability, and to build up documentation. Here you have the web URL to access to the website. What kind of data can you find in this MSDI? At the moment, the catalog gathers more than 120 metadata describing data about concerning imagery, such as orthophoto, hyperspectral imaging, acoustic data, or coastal photograph. We have also data concerning the physical environment, such as bathymetry, coastal feature or hydrodynamic, and geomorphology. We have data about biological environment. For example, we have data of the algae or corals, frequency of whales watching, coral vitality, or reef habitats. We have some data about recreational activities in La Réunion Island, such as diving or fishing or usage reserve. And finally, we have data about regulation. For example, you will find data on the limits of territorial sea or protected areas. Here it's a screenshot of this web portal. In this web portal you will find also a page to access to all the description about the thematics catalog that I mentioned before. If you click in this part, you will access directly to the metadata catalog, and you will find all the thematics catalog in this part with some description here. It's a classical metadata catalog. And then, if you want to display data, you can do it by using the GeoViewer application. And here it's data about imaging, hyperspectral imaging. Here I put an example of data about trajectories of turtles in southern Indian Ocean here. So to conclude this presentation, what I wanted to say that it was Inspire framework facilitate the development of a local SDI in La Réunion region. This allows on a new platform for the marine community, and it can be considered as the first link of an observatory of the Indian Ocean. Thank you very much for your attention. If you have any questions.
Yes. Questions? No question. Just one question from my side. You spoke about the different systems that expose catalog and metadata. The central catalog is an ingestion of the exposing catalog is collect all the metadata inside just one stage.
Can you
you present the different existing systems that are called joined in the central catalog service.
Yeah.
The existing catalog of each center is remain active, and the central keep the data from them, or there will be collected all the metadata in the central catalog.
In fact, all these catalogs are into the same architecture. Oh. So each project has its own catalogs, and then the global project, the Sextant Indian Ocean, collect and harvest all the small catalogs directly. Yeah.
Okay. No other questions? Then I will switch for the next presenters. Eero Hietanen. You should have here which is this one. Okay.
Okay. Hi everybody. Next we're going to move from seas to inland waters to Inspire Hydrographic team. Inspire Hydrographic team is two-folded, and content for it usually comes from 2 or more different data providers. We made a pilot in which we implemented Inspire view and download service for Inspire Hydrographic team. My name is Eero Hietanen, and others involved this project are Lassi Lehto and Pekka Latvala. First, let's take a short look at hydrography application schema and Finnish hydrographic datasets which it applies to. Secondly, I will talk about the actual implementation of this service, and further I will bring out some challenges we met there, and for the last I present one solution to which is about the update process of our service database. So hydrography application schema is divided in hydrophysical waters and hydronetwork schemas. Physical waters is designed for mapping purposes, and network schema is designed for spatial analysis and modeling purposes. Datasets INSPIRE Hydrographic team applies to are Finnish Transport Agency's shoreline constructions and canal logs, National Land Survey's topographic database, and Environment Institute's hydraulic network and drainage basins. Most of the features to physical water schema comes from a topographic database, and Environment Institute has made a hydrologic network model which represents this INSPIRE hydro network. We implemented this service using open source tools. As a database, we have PostGIS, and we use GeoServer to serve the data. An important component is GeoServer's application schema module, which executes the actual schema transformation. After loading the data to the database, we made some additions to the data types. The most laborious part was this configuring this app schema module, and SLD files we used for webmap service. In this kind of integrated service database, we have all the data in the same database in our national data models, and GeoServer and app schema module reserves the WMTS or WMS or WFS queries in INSPIRE feature type names or in INSPIRE harmonized layer names, and then app schema module recognizes the right features, and GeoServer can fetch the right features from the database. GeoServer returns, for example, INSPIRE valid GML if it's WFS query. So, findings about this implementation is that we were able to implement the INSPIRE compliant download and view service with using open source tools. Datasets we used in this implementation comprised the whole area of Finland, and the content was provided by National Land Survey and the Environment Institute. Main challenges I want to bring out are the compatibility of the data models and the update process of this service database. We made a comprehensive study about the compatibility of the Finnish data models with this INSPIRE data model, and we compared feature types, feature by feature and attribute by attribute. Although some of the features match very well, there are a lot of incompatibilities. There's no easy solution, of course, for that, but of course one solution in future is to develop national models better to better match the INSPIRE model. The second challenge is the update process of the database, which is separate from the original data updates. And to find a solution for that, we made a test implementation, or we studied OGC's geosynchronization service. And last few slides I tell you about our test implementation of geosynchronization service, GSS. The intention of the study was to find out if GSS is useful for this kind of multi-provider setting. Geosynchronization service engineering report was published 2010, and GSS has its origins in Canadian geospatial data infrastructures pilot, and the goals of the GSS are interoperability of the data providers, better access to the current data and avoidance of versioning and duplication of the datasets. Here is the basic idea of geosynchronization service. The publisher sends a change proposal to the service, and then the reviewer reads the change feed and either accept or reject the change. If the change is accepted, then the change is registered to this replication feed. Oops. And then the users of the data can read the replication feed. In our implementation, we reduced the model and left out the reviewer phase because as a data publisher, we have authorized data providers. So this is the this diagram shows the idea of our test implementation. And in the beginning, all the features of interest are replicated to the replication database, and the replication database may represent this integrated service database, or it can be a database in this kind of multi-provider settings where some additional information is provided on top of features of topographic database. The actual synchronization process starts when a topographic database is updated. The same changes are sent to this geosynchronization service, which logs the changes to the database. The user, which is the owner of a replication database, makes get entries query to this geosynchronization service and receives a replication feed which contains all the matching entities and matching changes. And then with custom-made management tool, the user can select all the changes he wants to send to his own replication database. Findings of this implementation are that it is possible to implement a change management database as a one PostGIS table with few columns. One column, WFS transaction column, contains the actual GML to execute the change. The service interface was implemented as a Java servlet, and it understands key value per request, and the main query is this get entries query, and there are several filters, those changes which can be used to get certain change entities. And the synchronization service returns replication feed in atom feed format containing all the matching entities. GSS has one more there. Our test client, or this management tool, was implemented with OpenLayers. This GSS has a lot of potential also beyond Inspire downloaded view services. Both of these, our test implementations were pilots, and we hope that they are useful when data providers are designing their services. So, if you have any questions, please be welcome. Here is my email address to contact. So, thank you.
Thank you. Questions? Yes.
The way that you update your data is only, what do you say, the core data model. So you update the geometry down in the basic database, and do you update the attribute as well?
Yes, in this our case, in our testing parameters, the both replication database and the topographic database are in same schema, but there are possibilities to add transformation between this updating process. So in our case, we can update geometry and all the attributes in this schema in the national model, but we could do also some kind of module there to make the schema transformation during the update.
Yes.
Hi, Jon Pil Hansen from Norwegian Hydrographic Service. We and the other parts of the Norwegian mapping service are experimenting with synchronizing, and we see lots of potential. Also, right now we are experimenting with the Coastal Administration Department to receive data from them about lights and navaids. So this can be used for quite a few different things, and we see lots of applications also within our own organization, perhaps within their organization as well, and so it has great potential, I think. Yes, so it was good to hear.
Okay,
thank you.
Thank you.
Yes.
Excuse my ignorance, but what is so crucial that it requires continuous updates in a hydrographic network? So I understand you map it first, and then what are the attributes that you require, or the geometry that is changing so fast that you require a feed to come in? Sorry, I'm not sure about that.
Okay. We have these separate databases. So and if they're going to live in production environment, then the update process doesn't have to be like in hour or daily, but it has to be once in a month at least to have because all the time new measurements are done in the field.
Yes.
So the point is, it's due to the localization of the measurements that you update the geography, and it needs to be so exact that you do it monthly. Would yearly be enough?
I really, that's not maybe what I can answer so well, but yeah, in some cases, but if we use this kind of service in other purposes, maybe it should be also good that there is. But yes, okay.
Okay.
It was mentioned in the previous talk or sessions that there was a certain river into a port in Belgium, I believe it was, that had to be, they actually measured the depth of that river every single day and updated it. So there are definitely things that can't be heard once a year.
Yeah.
Okay. Thanks so much. Next speakers is Jan Berg, Sonne. Okay, wait, this way. This one?
Yeah.
No. Yeah.
This is Ford and Berg.
This one? Which is the first? This one?
This one is.
Okay. Okay, this is your first one.
Well, yes, and now a completely different story. We heard about how to implement Inspire and distributing Inspire data. This is quite a bit the opposite way. We have a data set that we want to be used across different sectors with different administration levels, and we have to do something together with this one basic data set. And then we had an agreement on from the Ministry of Finance that we have to do this. And so what's in it is about something about how we create a hydrological digital elevation model with data from the river administration, and this is how the story goes. Jens Røyen had an introduction to this basic data for everyone, so I won't do much of a presentation about this program, but this is the Ministry of Finance who's actually found out that geodata is useful, and geodata is a driver for better administration and what do you say, e-government and transparency administration. So that's why we are working with this project, and it's a big program with a lot of programs, and we are somewhere situated down there. Oh, sorry. This is the one. What's it pointing? Yeah, it's a pointer. Yeah. So we are down here. Maps and geography has to be reused across the administrations. So we have this basic data for administration and climate adaptation. And what the driver is that we have correlate the use of data of rivers, stream data, and this has to be built on the basic data in FOS, what is the cartography database that is done by a common specification between the state and the municipalities. That's how they have one specification how to make cartographic data. So, and the problem is that we have authorities having river data, but they kept from themselves, and they do update it as a part of their own administration, and at the same time we spent a lot of money of making a cartographic database. So therefore we tried to do one data set for all the administration, and all the administrations should be in the future updating this data with the kind of knowledge in the field and correlating data from this administration. It could be more efficient and cost-effective to the climate adaptation efforts, because these things are overlapping. And of course, if you've got accurate data using the administration, there's a greater legal certainty for the citizens when they look into what the administration are doing and what data they are providing the citizens. So we, the state and the municipalities, are some kind of arranged marriage. We have to find out how to live together with this one data set, and we have to find out as well, are there any existing legislations that are there are the barriers from having a legal act that we have to use this basic data in our administration. And how do we in the future have a hydrological digital evaluation model that are correlated with this? So these are the short headlines for the next one, and I start with the climate change adaptation and what we have been doing of creating these Hietanen and the correction layer that creates the hydrological elevation model, and how we had managed to make these blue spot data which are essential for the climate adaptation planning, especially in the municipalities now. So what the correction layer is, that actually we have a digital elevation model, which is laser scans, quite accurate, and to use this we need to correct the elevation model so it can act according to how the water is moving on the surface. So there is a lot of bridges and pipes and buildings that we have to take into account when we have to model the movement of the water on the surface of a digital elevation model. So this is quite essential. What are the key components for a correction layer? And what we have found out that there's 8, I would say, key elements that we need when we are making this correction layer. So we actually make path for the water in the hydrological elevation model. So these are the terms that we've set on, and what has happening that actually we have a full coverage of a digital elevation model in 1.6 meters resolution. And what we did was the consultant firms who's been doing climate adaptation plans for the municipalities, they have been doing a lot of work of making their own version of this hydrological model. And we, after purchasing this kind of data, we asked the municipalities if they have any additional knowledge of where bridges and pipes and so on were, so we could add this in for the national correction layer. And so we managed to harvest all these data, and we managed to make elevation model in full resolution, and actually we did it in 2 versions, because sometimes you have to model water from the sea, and you have to model the fresh water, and then we have 2 models, one with the sluice closed. So that's when you use when you model the water coming from the sea, and vice versa. And then we made a full blue spot coverage model in this full resolution. The challenge will be, now we already acquiring a new laser scanned digital elevation model, and it's in its nature, or the scanning or the resolution will be 0.8 meters, so it's 80 centimeters per in resolution. So that's we have to find out or how do the correction layers going to fit with this new high resolution data. So that's the status of that. The next part has been going on for some time. It's a bit of discussion. I think this is kind of an arranged marriage, and we have find together these kind of different administration. How is this basic data going to work? How are we going, if adjusting the law, how is the content of this basic data when we are using it for administration across different levels? And how is the data model look like? In fact, the travel is, or the path that we are starting on, is that actually we have a quite dense and very precise cartographic data of rivers in Denmark. It's much more than you need for the administration. And these data are by this municipalities and the state are updated every 4th year. And they just put a new, what do you call it, a new decided paper on how they're going to work together. And it seems like they're going to update this theme every year. So that's challenged quite a lot if you have some administrations that's not are yearly based, or in fact you're doing it 6th year. How are these things going to work together, and how do we elevate these data for the use of hydrology? So one of the first tentative conclusion about is there any barriers in the use of these data in having a legal binding for using basic data? And it seems like that when you write a law of protecting nature, a law of water management, it's always like the text in the law, it's a legal binding, it's not the map. So actually we can do all what we want with data with some kind of a charter that says that yes, we are using this, but we not have to rewrite the laws of water management and nature protections to get the basic data to use within the administration. But there is one exception, that we have our law according protection of natural rivers, and in that particular law, there says that the map is the one that we are administrating on. So there is always a catch or something that run. So what we are trying to have been done is that we agreed on what is the basic needs and what are the perhaps data that could be useful, but it's not strictly necessary for the administration. And we agreed that if this is going to be useful, of course we have to have a hydrological network in the data, as stated in Inspire, with edge and nodes and direction. And this is the hard part, that we have to establish some kind of a reference systems between the basic data and the additive, the additional administration data that we link to the basic data. So how are we going to have the administration going on with all the knowledge that they have to use, and how are we going to link these data with the central basic data? So, and that's quite tough. And some other things that we have to we want to do is registration of this water subways, pipes, bridges. We want the dimensions of these, because these are essential for the climate adaptation planning. So we need to know how much water is capable of flowing with all these pipes and bridges that we have in according to this river model. And of course, another thing is that the catchment areas is some kind of an old shape, or it's not been updated for quite a long time. So, and we got this wonderful new high-resolution digital elevation model, and as well as a hydrological elevation model. And that is questioning, are we going to remodel the catchment area because we got so high value information in the digital elevation model. But that would have some impact on all the work that they are doing in the water frame directory, because the water frame directory area and the way you model and the way you try to find out impacts on ecology and so forth, you use these catchment areas to find out how and when and how much and what are we going to do for the next 6 years in this one. And that's trying to find the right time to do the transformation to use all this lovely high quality data that we actually have. So what we are facing is that we have these 3 types of registrations in the administration. And we got this type 1, which is mainly from the municipality, or the public streams as we call them. It's the yearly or the daily management of having the water flows in the rivers. So they cut the weeds and stuff like that, and that's according to the rural management or the farmers, that they want to get the water as fast as possible away from the field, so they can get as early as possible to do their jobs on the fields. And then of course we have the water frame directory, and then we have another part in natural protection. That's with some natural streams that's originated the historic or the real natural streams have a 2-meter buffer zones to protect the rivers. And of course we have a registration of all these natural and nature protected where we have all this ecology and nature. And of course all the rest is interesting according to climate adaptation, because this is where the water flows and we want to know where it flows. So, and then on top of this we have implemented a protection zone that covers the type 1 and 2 that are meant as an implementation of the water frame directory, that the farmers have to stay, or they're not allowed to do their farming in 10 meters from the water bank. And we just have this later. We have just revisited, or they have just made a new law now that it's including these one, and so that's another challenge, that these data are going to support this administration as well. So what we're facing is that we have to have this basic data, and we have all these kind of administrations that have different laws and tasks to do, and we have to find out how are we going to manage to link these data to the basic data. So what we have done now is that firstly we find out that a basic model that includes the criteria for the basic data model, and they creating the basic data program. They have lined out some basic requirements for data models when you're working with the basic data model. So that we have been implemented. And what we're going to do now is find out in testing areas, how do we create this reference layer, this reference systems that could connect the administration data with the basic data. And of course, one of the big issues is what would the impact of the water frame directory plan when we update the water bodies. Because when you're changing the geometry, the length of the geometry is changed, and the whole economical plan for implementing the water frame is based on how many kilometers of river are we going to change, or doing some economical plans for nature restoration, changing whatever. And that's and another thing is that these huge cartographic data has a lot of what you call loose water bodies that's not connected, because I think 95% of all rivers in Denmark are regulated, in fact, and a lot of due to agricultural business, they have piped and drainage huge areas. So actually, all these loose water bodies is in fact connected by a drainage system. So do we need to connect all these loose water bodies? And that's quite a lot. And of course, can we build a target architecture that will bind all these data together in this basic data model? So just what we have here is not the Inspire model, but of course we have been using the same techniques, especially when working with the basic data, that they are using a lot of issues from the Inspire data model, and we as well are Danish. Using a lot of the same attributes and entities from the Inspire. So that's quite a good correlance between these the Inspire specification and what we are trying to create on the basic data model. So, and one of the challenges of this data management is that what we have here is actually some basic data. And here we have some administrative data. That's when you use in some administration they have, split the files to register the administration knowledge or data. What happens if you actually do a nature restoration project when you rewind the river? How do we keep the administration data that is connected to the river bodies? So that's one of the. Can we make a reference system that supports this? That's the challenge. But some administration are using linear referencing, and the question is that suitable, or is it? Can we use this as a principle, but then we have to do like a convergence that we all agreed on using linear reference in all administration levels, and this is we have to find out if that's really the path to go. So in some way, it's like we have a lot of administrative data, and we have either to do some river reference that we all connect our administration data to, or we have to find out how, if these data are connected directly to the river segments, how do we update and show and whatever these data in a common in a future architecture environment. And just to give you imagine that that's the first draft of how we could see some kind of a ESB running here that could deliver and find out who is asking for what, and all the services is well defined, and all the systems are actually connected through this architectural ESB. And the question is, how many services we have to build to make this huge connected service system working? So that's how we stand, and that's a challenge, and we, hopefully in the future, will solve these problems. That's it.
Yes.
I'm Maria Val from Portugal.
Yes.
I think it was a very interesting presentation, and I would like to ask you, because the Water Framework Directive dealing namely with drinking water concerns, and within the Inspire context, is a quite relevant issue for main countries and for our country as well. What would be the priorities that you would selected in order to make a better approach of the Water Framework Directive to deal with water management problems in what concerns of data collection, and what the data collection from your experience could show you that some things should be addressed in a much more proper way, because I think that now you are very well aware of what is not put it right into place. Okay.
Yeah.
Thank you.
I think I understand your question. That's what we have seen is that the inspired data model is not, and the part of the Water Frame Directory is that's actually in the hydrology draft is not covering all the needs that we have from running our administration, and all the, as you see here, all we have of all the surface water monitoring that we have here is not really, it's not stated out clearly how we connect these things. So that's just the thing. I don't know if it was the answer to your question.
I was also considering what you just said in terms of watershed management and covering all the data. How to go through water management within a country as a whole instead of managing only the watershed, having only the watershed approach and some other problems like, for instance, the 10 meters, why 10 meters, why not 100 or whatever.
Yes.
Things like that. I think that that's one of the work
Yeah.
that perhaps you can control later.
Yes? That would be nice.
Yes.
My name is Nicholas Hagemann. I'm from the University of Bonn in Germany. I see a good connection to the Water Framework Directive with your work, and maybe you can't change anything in this cycle of the Water Framework Directive, but the first cycle ends in the next year, so maybe for the next 6 years you can do something. And I also see a lot of potential for the Floods Directive. I mean, there's a question if you used your elevation model for the making of the hazard and risk maps last year, and maybe for the flood risk management plans that have to be set up. There is probably a lot of synergies in using this system.
Yeah, we used this digital elevation model to create what you see sea on land flood model for the seawater, and we use this as well for a flood model for the rivers in the flood directive as well. So pointing out we pointed out 7 risk areas, and we used these data to map these 10 areas that we have in the flood directory. And as well as, and at the municipality levels, we have implemented a law that the municipality have to do a climate action plan on the local level. So, and they're using this data as well. So in that way, we reuse all these data in the planning right now.
Yes.
Thank you. Camille Kitman, University of Manchester. I'm just wondering, how was the DM created at 1.6 meters?
Laser scanning.
Laser scanning,
Yeah.
aerial.
Yeah, aerial laser scanning.
Excellent.
So, and now they are flying at this moment for the next generation.
Oh, great.
I think they're passing in these together. So don't look
It's
up.
passing it.
You will be beamed. That's it.
Okay, thanks so much.
Yep.
And Edgar Barrera is not in the room. No. Okay. Then we jump in the last presentation. Xabier. This needs one. You have those. Okay.
Yeah. All right. Good afternoon, everyone. My name is Xabier Erana, and I come from the Finnish Geodetic Institute. And my topic will continue what the very last presenter already explained to us, which is very good because it gave you some very detailed introduction, which I really appreciate. And I will continue that path, perhaps from a more practical perspective. I will show you a little test we carried out, and we considered what would be the potential of the airborne laser scanning or airborne LiDAR for the possible hydrographic data update or revision. The subtitle of this session is From Sources to the Seas. I will focus on the very source from two different perspectives. One, because the data elements are the key and the source element of a data infrastructure. And secondly, because I will concentrate in the very source, in the headwaters, in the data sets or data collection where the greatest amount of flaws are currently. So I want to share three ideas with you in order to position ourselves in the topic. The first one would be that the small basins with low order streams comprise the majority of our surroundings, of the stream length in total in the European Union and as in the rest of the world, and very little or not enough is known about those small rivers. In that regard, I would say that conventional methods do not support the current users and the legal requirements. We have already seen in quite a lot of presentations that data is at the moment far from being perfect. And thirdly, I would say this is the thematic scope of the hydrographic data specification guidelines, which says that theoretically, or the scope would be to provide a solid interoperable framework for mapping, reporting, and modeling purposes. As you already know, this is not with the conventional methods in the headwaters. This is not the case. So this is how the hydrographic features have been extracted in the last 40 or 50 years. This is a stereo plotter, a technician working on a stereo plotter. And what is the current condition of the hydrographic features at the topographic database of the National Land Survey of Finland? Well, their motto is that we have a topographic data for a multitude of uses. I don't doubt that. The scale they work on is from 5,000 to 10,000. And I have to say, I have already heard this morning that hydrography is a low priority topic, and I would say the same about the data and the entities. Although there are several other feature classes which are continuously or yearly updated, I would say that hydrographic features have been at the backstage and have nearly very little been updated, at least in Finland. In Finland, you know that Finland is the country in Europe with the greatest forested areas. It's rather challenging to capture the hydrographic features in some instances. And, well, there is a lot to improve, let's say so. So what does the inspired data specification on hydrography tell us about the data quality? Well, it applies the ISO standard 19138, which has now recently been updated, but basically it tells us the same. We have the 5 elements: completeness, logical consistency, positional accuracy, thematic accuracy, and temporal accuracy. I will focus in completeness and positional accuracy and tell a little bit about temporal accuracy, because this is all about updates. So there are 2 sort of data quality documents that the topographic database has, which defines a water feature as a feature of permanent or temporary water. There is no distinction between perennial, intermittent, but instead there is a categorization which is surface and subsurface water level. We have wider than 5 meters, which would be called polygons. We have features of between 2 and 5 meters, which are polylines, and those which are narrower than 2 meters and are only exceptionally captured in case of a, let's say, continuous network, which is the case of ditches. Finland is full of marshlands, and these marshlands are always drained, or forest ditches or marshlands are ditched or drained by these ditch networks. So I will focus in these last 2, because here is where we find the greatest amount of errors, the greatest amount of inaccuracies. And we have the second data quality specification, which is the data quality model, first made in the 1995 and later updated in 2006, which says that all features that have been captured by this stereo plotter are theoretically good in visibility, number 3, and the positional accuracy, which was updated in the year 2006, they promise us that the average is 5 meters. So we already got some introduction regarding the laser scanning technique. Basically, it is a remote sensing technique that captures the objects and sides of a surface, the interaction between 2 components and the surface makes it possible, this capture. One would be the actual laser scanning, which measures the distance to the ground, and the GPS or IMU would deal with the exact or accurate positioning. So here we have the current picture of the airborne laser scanning data campaigns in Finland, nearly completed. Only few areas left in Lapland and some coastal areas. And for the test that we've carried out, we've used 2 data sets. You will see a little later on, we have used the reference data, which is our institute's own data, which contains millions of points. These are all the points, so then of course we would have to extract only the ground points to make the digital elevation, and we also have got the National Land Survey's airborne laser scanning data. This is one of the many things what we can get out of LiDAR data. This is a so-called mod or modulus, which somehow represents the altitude variation in a centimeter level. So this color, full color range that you see from purple till next purple would be a 5 meters elevation difference. And if we would approach, or if we would zoom in, you would be able to really locate or see the pattern very clearly. This is a plane where elevation differences are very, very small, and you are able to see what are the differences and even very clearly locate from where the actual river delineates. And the same in this ditch area, for instance. So, but of course, as every other method, the airborne laser scanning has its own flaws, its own limitations. The first one, the forest canopy. We all know, and especially in Finland, where most of the forest is coniferous, that is quite a bit of a challenge, because it cannot penetrate, or at least it cannot penetrate as well as we wished. The second limitation would be the plane. As you saw in the previous slide, it has an accuracy of approximately 15 centimeters, and 15 centimeter in a plane can mean one hell of a change in a river routing. So it simply goes crazy. We will see later on. Detailing is also a problem. It is great to have details, but of course the problems or the details in the topography that Corsair data simply omitted now are captured, and therefore we have detail-related problems that we didn't before. And of course, human impacted landscapes. These are, as the previous speaker said, real challenge, because automatic delineations don't recognize breaches, don't recognize human impacted infrastructure, and therefore that needs further adjustments. And one more limitation would be that flow extraction is only based on drainage area. This works relatively accurately in nature, but again, when there is a human landscape, such as a ditch, results don't make sense, because of course we all know where the ditch ends, and the ditch, if the drainage basin ends at this point, at the ditch is here, we know that the water would end in here. But if the drainage basin continues all the way on this left-hand side, the logic would be, the airborne laser scanning would tell us that the river continues this way, when we all know that it is in this location. And then another question would be, where do channels begin? This is also very easy in human impacted landscapes. We all know where the digger stops, but where does the channel begin in the natural landscape? So we carried out a small test. We created a reference data with our FGI airborne laser scanning to test first the completeness, and secondly the positional accuracy by means of this VRS GPS that permitted us to locate into a centimeter accuracy the position of each center line. So with all this, once the reference data is created, we first test the National Land Survey's airborne laser scanning data, and also the current database's hydrographic features. So the test works as following. We have the airborne laser scanning data. This data is calibrated and classified. We only select the ground point data. There is a 1 meter grid data and digital elevation created. Then we, the hydrologic modeling with flow accumulation and direction is carried out. We extract the vector data, and this data is manually adjusted with further products that the digital elevation model gives us, such as the modulus image that you saw before, such as the hill shading, the orthophoto, and still the manual data editing for removing all the breaches and further obstacles. And on the other hand, the positional accuracy, we went to the field and strategically selected certain points in the area. This is our study area. And we will test the positional accuracy of the rest of the data by means of these points. So this would be the test data. We have the National Land Survey's airborne laser scanning ground points. Again, the same procedure, 1 meter grid, 1 meter grid, digital elevation model, hydrologic modeling. We extract the vector data, and at the same time we extract the current features from the topographic database, and we make a comparison with the reference data for both positional accuracy and completeness. This is a 1 meter grid data, and I said it wrong. The reference data is 0.25 meters. So this is the completeness test. You can see that our reference data is buffered into 10 meters, and the NLS, ALS is in red color, and the current topographic database streams is in blue color. So this might look a little bit confusing, but we can already see what it has been said before. This is a ditch area, and you can see the reference data has this square type of shape, and the airborne laser scanning goes crazy in a plain or in a flat area and simply draws a completely different pattern. We can also see, by means of this picture, that airborne laser scanning permitted to capture certain features that were absent in the topographic database. This would be the errors of omission that are mentioned in here. And then we go to the positional accuracy. And the question here is how to compare and assess the similarity of the polyline test sets. If they were points, it would be easy. But when it comes to polylines, things get a little bit tricky, because it's not easy to say those two lines, when they start and end in a different location, how do you compare them? So what we did is we converted all the vertices of these polylines into points, and the closest point from all was compared to the actual reference data for positional accuracy. This is our test field. All the rivers, roadside ditches, everything what we consider to be a perfect data, or our nominal ground. And this is the data sets that we used: the airborne laser scanning, the digital elevation model, all the sub-products that we get out of it, field verification, the actual database for verifying certain things, and the VRS GPS points. And what are the results? There has to be a difference between 3 zones in order to understand the results. We have an area in which airborne laser scanning has a great potential. This would be an area where regular valleys, quite forested, can be clear, quite forested, but there needs to be some sort of inclination, gentle slope at least. In these areas, the RMSE can drop in average up to 1.9 meters. We have areas in which it could be a lot improved, areas, plains. But luckily, these areas can be a lot improved with the help of orthophotos, because there is no forest, there are no trees. And then we have areas like ditches, in which, well, things are a complete mess. That's why differentiation is a must in this regard. And what are the results for the topographic database? We have found no errors of commission, and there you can see that there is a star, because the actual ditch system was created in the 60s and 70s. And I think that every national mapping authority has a rule that no errors of commission should exist. But because of this drainage or because of these ditch networks haven't been updated, and in many cases some piping has been introduced, already the nature has started to take back these places. And when we visited the field, we could see several places in which it's rather complicated to classify them between, is this a ditch, or perhaps it used to be but not anymore, or so what is it? So that's why there is a star. But we found some errors of omission, which represents the 15% of the database's current network. You can see that if we consider these errors of omission, the RMSE values are simply completely wrong. If we don't consider those errors of omission, you can see that the RMSE values fulfill the 5 meters that were specified in the data specification. So these are the errors of omission. You can see the red lines. Some of them are obvious, as this one, and some other are important because you can see before looking at the topographic database, these lakes seem to be isolated. No connection between the lakes and the current river network, and the airborne laser scanning has been able to detect that such connection actually exists. And the same thing over here, well, small details, but that would be the point. And here you have the corresponding pictures. And data referred to the positional accuracy. This is the purple color represents our reference data, and the blue lines represent the current topographic database. And here you can see what are the values of RMSE in positional accuracy. And even in the ditch areas, you can see that the numbering, when the ditch and the forest both are combined, the inaccuracies get rather big, as you can see in this area. So to conclude, we think that the airborne laser scanning has the potential, brings the opportunity to take the data capturing into the next level. As you have seen already, the fully automatic delineation is not possible. So the solution is always the combination of all existing methods, the state-of-the-art and the more traditional ones. We think that the channel initiation should be a thing to consider in the future. We have now considered that the database's initiation point is relatively correct. There could be a lot of more information about it. Intermittent, perennial, some dash lines maybe, I don't know. And perhaps the numbers regarding completeness may have been misleading, but you need to understand that the database features are the final product and ALS features or ALS results are initial products or initial results. Those results need, of course, further adjustments with the help of the rest of the data we've got. And still it gets superior results under demanding conditions. So that would be all. I think this airborne laser scanning brings the opportunity to bring the end user the quality that many large-scale applications deserve. Thanks.
Yes, no, thanks. Questions? Yes, I'm sure you have a question.
I was wondering, have you used the topographic database to kind of adjust the digital elevation models in the directions when you model and remove the sinks in the model to do the flow accumulations model?
We have used it as an orientative product.
Yes.
Let's say so. Yes. But of course not touched for the reference data. Mm-hmm. Otherwise it would be contaminated.
All right.
So it is an orientative product in a way that it is a reference, better or worse. And when we visited the field, the ditch network, it has been a rather big challenge to map these ditches. Unfortunately, I don't have the pictures because I thought this was a 15 minutes presentation. But yeah, it has been a big challenge, and the database information has been helpful in that regard. Yeah.
You just reported to us about a pilot test. Can you predict when such methods go into production in Finland?
When?
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 Well, is it in 5 years, in 10 years, or whatever? What is? Do you have any adjustment?
I think it is very soon.
Really?
To you, yeah.
Nationwide?
Yes.
All right.
Yes. That is the idea.
And could you be a little more specific about very soon?
It's difficult to say, but I know that because we have already reported our results, and in a way the results are what it was expected to be. I think that in a few national mapping authorities already have used at some point, not in such landscapes, I think in more small scale and more related to urban studies, but I think it is going to start very soon, and the database and the data system itself are now in a process of change. These are, of course, this I forgot to mention, but this hydrographic data is made for only cartographic visualization purposes. Then we have the agricultural ditches that are maintained by the Ministry of Agriculture and Forestry, and also, as my colleague said, there is a data set from the Environmental Institute. There is now, I know that the database and the data system are going to undergo quite a big change, and all this data, as our previous speaker said, is going to be fusioned. And I think the airborne laser scanning will be used for this reference data creation. And if I understood correctly, we will see that happening within the next 5 years, or even sooner.
Okay, other questions? No? Yes. Sorry.
There is. Did you use the lasers in any hydrographic surveys, like the lakes or the shores?
No.
You did not?
No. Not this time.
Okay.
Maybe in the near future. But no, the scope of this project was simply the let's say the headwaters in the sense of first order or second order rivers. But I know there is some intention to extend it into bathymetry and other applications.
No other questions? Thanks so much. Thanks to all the attendants. I apologize for the missing of the presentation of Edgar Barreira. That is not presented. We hope that there are no so critical problems. And now it's time for lunch. Thanks so much.